In this video, we will discuss pulleys and Atwood's machines, a common application of Newton's second law and the process we have used so far to solve all force puzzles. The Atwood's machine consists of two objects, like blocks, that are strung over a pulley wheel and then allowed to move. We assume the wheel is frictionless and that the string and the wheel are massless. That way, we don't have to worry about the presence of the wheel altering the motion of the blocks. We also assume the tension is uniform throughout the string. Since two objects are moving, we need to track their motions with two different free body diagrams. The forces on each block will be different, but the sizes of the accelerations of the blocks must be the same. If the blocks had different accelerations, the string would either bunch up or snap. Consider this puzzle. A 1 kilogram block and a 2 kilogram block are connected by a very light string. The string is passed over a very light, frictionless pulley wheel. What is the acceleration of the blocks? And what is the tension in the string? In this question, we were shown a 1 kilogram object which was strung over a pulley wheel, something like this, and connected to a 2 kilogram object. Now, if you were just to let this go, the 2 kilogram object is going to start accelerating downwards, and the 1 kilogram object is going to start accelerating upwards. And the pulley wheel is going to rotate in order to change the direction of the tension so that these two will be connected to one another. Their motions will be related to one another. Now, one thing which we have to assume if we want to solve this question is we need to assume that this pulley wheel is very, very light. So it is virtually massless. Otherwise, you won't have these two tensions equal to each other. And that is an important assumption that we're going to make in this question. Now, let us draw the free body diagrams. For the 1 kilogram object, there are two forces. I will represent this object as a spot. There is the force of weight that would pull down, obviously, and the force of tension that would pull it up. And for the 2 kilogram object, we would have a different free body diagram. Again, we have the weight pointed down. I'm going to represent this object as a spot also. And we have the tension pointed up. But the thing which is different over here is that these two things have different masses, so clearly they must have different weights. I'll represent this as weight 1, and I'll represent this as weight 2. So the fact that they have two different weights is the reason why we can't draw them as part of the same free body diagram. They are effectively two different objects with two different characteristics which are moving in two different ways. So they need two different diagrams. Now, let us set origin and axes. In a free body diagram, the spot is always the origin. I'm going to set my positive y-axis this way for the 1 kilogram object. But, and here's the trick, I'm going to set my positive y-axis this way for the 2 kilogram object. Now, why would I set them in opposite directions? The answer is because this one is moving upwards, and more correctly, it's accelerating upwards, whereas this one is accelerating downwards. So, because I can set my axes whichever way makes this question easiest to solve, the way that makes it easiest to solve is in such a way that both of the accelerations end up being positive. So this way, if this object is accelerating up, it feels a positive acceleration, and since this is accelerating down, I still have it as a positive acceleration. We will have to be careful about it when we set up our force balances, but this will make this question overall easier to solve. Now, let us set up the force balance for the 1 kilogram object. So for the 1 kilogram object, there is a force only in the y direction. The total force is going to be composed of the tension, which is pointing in the positive direction, minus the weight, which is pointed in the negative direction. But total force is equal to mass times acceleration. Therefore, the tension plus the negative weight is equal to mass times acceleration. Now, how do we figure out the total weight? The weight is given by mg. The mass of this object was 1 kilogram, and g is 9.81, which works out to 9.81 newtons. That is the weight of the 1 kilogram object. We now take this information and we put it into this equation over here to give us tension minus 9.81 is equal to mass times acceleration. So we can simplify this to be tension minus 9.81 equals the acceleration. Now we notice that this is one equation with two unknowns. This cannot yet be solved. We need more information. So now we need to take a look at the 2 kilogram object. Now, let's take a look at what is happening in the free body diagram for the 2 kilogram object. The 2 kilogram object feels forces only in the y direction. The total force is given by now weight 2 in the positive direction, and the tension is in the negative direction. Now, we know that this is going to be equal to the total force, but the total force is equal to mass times acceleration. So, weight 2 plus negative tension is equal to mass times acceleration. Now let's solve for weight 2. It's equal to mg, which is equal to 2 times 9.81, which is 19.62 newtons. That is the size of the weight force. Take this and put it in here. 19.62 minus the tension force is equal to mass times acceleration. Now, we have now a second equation that relates together the tension and the acceleration. And the thing which is important over here is that the way that I've drawn it, the acceleration of 1 and the acceleration of 2 are equal to each other. How do we know? Because if the two accelerations were not equal to each other, the string would either bunch up or it would break. The only way that the string can remain taut the whole way through is if the two accelerations are equal. And as I mentioned before, if the pulley wheel is light, then these two tensions are equal as well. So we now have a second equation that has a second unknown, that accounts for the two unknowns. Now, let us take the earlier equation that we had and let us plug it in for the tension over here. Now, rearranging the earlier equation slightly, we get tension is equal to acceleration plus 9.81. Take this and plug it in over here. We get 19.62 minus acceleration plus 9.81 equals 2 times the acceleration. Rearranging this and simplifying, I get 19.62 minus 9.81 gives me 9.81. I can subtract the acceleration here, That gives us 2a. And therefore, 9.81 is equal to 3 times the acceleration. The last step over here is to divide both sides by 3. So, 9.81 divided by 3 gives us 3.27. So the acceleration is 3.27 j hat meters per second squared. Now that we solved for the acceleration as being 3.27 meters per second squared, we can take this value and plug it into this equation over here to solve for the tension. So the tension minus 9.81 is equal to 3.27, which means the tension is equal to 13.08 newtons. Now, the direction of the tension is different for these two objects. So, correctly speaking, I should put this in absolute value. But the tension upwards on the 1 kilogram object will indeed be 13.08 j hat newtons, and the tension in the negative direction over here will be negative 13.08 j hat newtons. So we have successfully solved for the acceleration and for the tension in the string for this pulley system.
Another type of Atwood's machine involves two tied blocks where one block dangles from the wheel but the other is placed on a table. The dangling block falls to the ground, and as it does, the block on the table is dragged forward. Consider this puzzle. A 2 kilogram block and a 4 kilogram block are connected by a very light string. The 4 kilogram block is placed on a frictionless table. The string is passed over a light frictionless pulley wheel that is attached to the edge of the table. The 2 kilogram block dangles over the edge of the table. What is the acceleration of the blocks?
In this question, we were told that there is a ledge, like the edge of a table or something like that. Here is a 4 kilogram object. There is a pulley wheel here. And the 4 kilogram object is roped over the pulley wheel to a 2 kilogram object. Like that. Now, if we were to analyze the motion of these two objects, we would need to draw two different free body diagrams, because the 4 kilogram object would require a different free body diagram because it's feeling a different balance of forces from the 2 kilogram object. And also, just in general, it's good to have different free body diagrams for different objects. So, let us start with the 4 kilogram object. The 4 kilogram object is going to feel a weight force down. Let's call it weight sub 4 for the 4 kilogram object. A normal force up, and a tension pointing to the right. By contrast, the 2 kilogram object feels only two forces. It feels the force of its weight downwards. Let's call this weight sub 2. And it feels the tension upwards. Now, the same rule applies in this sort of question as applied in the pulley question. The tension in the rope must be consistent because the wheel is light. And these two objects have to have the same acceleration because the string is not bunching up and it's not snapping either. We will use that information later on. For the moment, let us draw the axes on this free body diagram. I'm going to set the origin for the 2 kilogram object at the spot, as always, and I will set downwards as positive. For the 4 kilogram object, I can also set downwards as being positive, just to change things up a little bit, but more importantly, I will set rightwards as being positive. So now that I have my origin and axes, let's start by drawing out the balance of forces for the 2 kilogram object. For the 2 kilogram object, in Y, the sum of the forces works out to weight downwards and the tension force upwards, which is in the negative direction, so I have to write it like this. The total force is going to work out to mass times acceleration. So putting these together, we get weight 2 plus minus tension is equal to mass times acceleration. Now, we can solve for weight 2, which is equal to mass times gravity. Mass, 2. Gravity, 9.81, which works out to 19.62 newtons. Remember, that is the size of the weight force. Now, the mass of this object was 2 kilograms, so I'm going to take this 19.62 and I'm going to plug it into this equation over here. Simplifying it a little bit, I would end up with this. 19.62 minus tension is equal to 2 times the acceleration. Now, that is as far as I can get with this particular equation. I suppose if I wanted to isolate the tension, I could do that. So move the tension to the other side, move the acceleration to the first side. So you'd end up with 19.62 minus 2 times the acceleration is equal to the tension. And maybe that will come in handy in the other direction. Now we've solved for one of the relationships between tension and acceleration. Now let's take a look at the 4 kilogram object. Now, the 4 kilogram object is going to be dragged rightwards. It's not going to collapse into the surface, and it's not going to levitate off the surface. So that means that there is no acceleration, and therefore no net force occurring in the y direction. So we don't need to really bother ourselves with the normal force or the weight force. But we do have a tension force. So let's examine what is taking place over here. In the x direction, the total force is equal to the tension force. And since the tension force is going to wind up being equal to mass times acceleration, because total force is also equal to mass times acceleration, we can substitute the mass over here and get tension is equal to 4 times the acceleration. Now, we were told from the earlier part that 19.62 minus 2 times the acceleration is equal to the tension. So this is where we ended up when we analyzed the motion of the 2 kilogram object. We have tension in both of these places, so we can substitute for A in both. 19.62 minus 2A is equal to 4A. Add the 2A to both sides. 19.62 is equal to 6A. And so we get an acceleration equal to 19.62 divided by 6, which is 3.27. Yes, it's the same acceleration as we saw in the pulley problem. I will put this as the size of the acceleration, because if we want to be absolutely rigorous, the acceleration of the 2 kilogram object is in the positive y direction, so that's j hat, but it's in the positive x direction for the 4 kilogram object, which would be I hat. Regardless of the direction, however, the size of the acceleration is 3.27 meters per second squared in both cases. As for the tension in the string, well, we see up here that tension is equal to 4 times acceleration. So tension is equal to 4 times 3.27, which is equal to 13.08. That is the size of the tension force.
That last question can be spiced up a bit by adding friction. Consider this situation. A 1 kilogram block and a 5 kilogram block are connected by a very light string. The 5 kilogram block is placed on a table with a rough surface. The coefficient of kinetic friction is 0.05. The string is passed over a light, frictionless pulley wheel that is attached to the edge of the table. The 1 kilogram block dangles over the edge of the table. Once the system is moving, that is, once we're in the realm of kinetic friction, what is the acceleration of the blocks?
In this variant of the puzzle, we have 5 kilogram object on a table. We have a pulley, and the 5 kilogram object is strung to a 1 kilogram object, which is dangling off to the side. This 5 kilogram object is subject to kinetic friction. We were told that the coefficient of kinetic friction was 0.05. The 1 kilogram object will fall like so. The 5 kilogram object will be dragged like that. Now, let's draw the free body diagrams. For the 5 kilogram object, which I will represent with this spot over here, there is of course the weight down. There's the normal force up. There is the tension pulling it to the right. And finally, there is kinetic friction, a small force of kinetic friction that is hindering it and pointed to the left. What about for the 1 kilogram object? There is a weight pointed down and a tension pointed up. And that's it. Now, let us set origin and axes. For the 1 kilogram object, the origin will be at the spot, as it always is. Downwards, I shall set as positive y. For the 5 kilogram object, I shall set rightwards as positive x and upwards as positive y. Now, let us solve for the various forces involved here, or let us use Newton's second law to figure out what the tension and the acceleration would be. So, for the 1 kilogram object, in the y direction, the total force is given by weight plus the negative tension force. But total force is also equal to mass times acceleration. So, weight plus negative tension equals mass times acceleration. Now, when we're talking about the weight here, we're really talking about the weight of the 1 kilogram object, which I can distinguish by calling it weight sub 1 as opposed to weight sub 5. So, this would be, let's calculate what that weight is. The weight of the 1 kilogram object is given by mg, which is equal to 1 times 9.81, which is equal to 9.81 newtons. Now take this 9.81 and put it in here. 9.81 minus the tension. I know I'm being a little bit loosey-goosey as far as the symbolism goes here, but let's run with it. We're just finding what the positive value of the tension is equal to the mass times the acceleration. So rewriting this, we we would end up with 9.81 minus t equals a. Let us start with this equation, and we will use this equation a little bit later on. Let's store it for now. Now that we've examined the 1 kilogram object, let's turn to the 5 kilogram object. For the 5 kilogram object, we have a force of kinetic friction at work. And if that's the case, we need to find out how big the normal force is. So let's solve for what's happening in the y direction of the 5 kilogram object. For the 5 kilogram object, in the y direction, the total force is equal to the normal force minus, or the way I should say it is plus the negative weight force. So this total force is equal to mass times acceleration. So we now have normal force plus negative weight force is equal to mass times acceleration. Now, the weight force, the size of it is going to be given by mg. Now, the mass is 5. G is 9.81. That works out to 49.05 newtons. Again, I know that because I'm a nerd. So let's plug this in here. The normal force minus 49.05 is equal to the mass, 5 kilograms, times the acceleration, which is unknown. Or sorry, this is the y direction. The acceleration isn't unknown in the y direction. The acceleration is 0 in the y direction. So we end up with normal minus 49.05 equals 0. So the normal force must also be equal to 49.05 newtons. And if we want to be particularly rigorous about it, we would say 49.05 j hat newtons. The mistake that I had made earlier was in that the acceleration in the y direction is known. Why? Because in the y direction, this 5 kilogram object is not collapsing into the table, and it isn't levitating off of the table. That means that there is no motion in the y direction, which means that the acceleration is 0. So the acceleration in the y direction is known. It's the acceleration in the x direction, which is unknown. And that is what we are going to solve for right now. For the 5 kilogram object in the x direction, the total force is going to be given by the tension pointing right minus the force of kinetic friction pointed left. Total force is equal to mass times acceleration. So putting these together, we get tension plus the negative force of kinetic friction is equal to mass times acceleration. Now the tension is unknown, but the force of kinetic friction can easily be solved. It's equal to the coefficient of kinetic friction, which is given to us, times the normal force. That is 0.05 times 49.05, which works out to 2.45. So that's the size of the friction force, 2.45 newtons. Let's plug that information into this equation here. Tension minus 2.45 is equal to the mass, 5, times the acceleration, unknown. So this is now our second equation. Now, from earlier, you'll remember that we said that there was another relationship between the tension and the acceleration, which we got from the 1 kilogram object. 9.81 minus the tension equals the acceleration. let's put that in over here. If 9.81 minus tension equals acceleration, then I can plug that in and I would get, or let's try rewriting this to isolate the tension. So that would give us tension is equal to 9.81 minus the acceleration, plug that in over here. 9.81 minus the acceleration minus 2.45 equals 5 times the acceleration. 9.81 minus 2.45 gives us 7.36. So now I have 7.36 minus the acceleration gives us 5a, or I can add the acceleration to both sides. I would get 7.36 is equal to 6a. So dividing both sides by 6, I get an acceleration of 1.23 meters per second squared. .23 meters per second squared. So now, the last step is to find out the tension in the rope. Since we've already found out the acceleration, 9.81 minus tension gives us the acceleration, 1.23. We can solve for the tension by adding it to both sides and subtracting 1.23 from both sides. So that would give us 9.81 minus the acceleration, gives us 8.58 newtons. So that would be the tension. This would specifically be the absolute value of the tension. And the reason for that is because the tension is pointed in two different directions for each of our objects. It's pointed in the positive x direction for one, but the negative y direction for the other.
In this video, we looked at pulleys and the Atwood machine. In the next video, we will explore ramps, and we will see how pulleys can be used in concert with ramps.